Friday afternoon.
Okay, so we are online on YouTube. Okay, good.
Okay.
So, welcome to the last talk of today of Majorana-Raychaudhuri seminar series. And our last speaker is Dimitrios Karamitros.
Perfect.
And he's going to speak about how to simulate action-like particles and cosmologies. So maybe I'll send you a reminder when 5 minutes are left.
Okay. Good. Thanks for the invitation. Thanks for everyone who is here. I will talk about kind of a passion project for me. As you can observe, it's been, I mean, a year and 2 years in these two publications, but I'm still working on this. So what we see is basically two things. One library that basically solves the action equation of motion under the standard misalignment mechanism, and another library that simulates non-standard cosmologies in general, the standard cosmological background plus an extra field that decays and deposits some energy in the plasma. And the two libraries, of course, can communicate, and you can use them both to simulate action-like particles in non-standard cosmologies in general. So I will talk about all of these things. Don't worry, it shouldn't take too much. But first, we should start with the obligatory dark matter slide. So first, as you know, we don't really know much about dark matter. We know that it interacts gravitationally, and we have a good idea that it's electrically neutral, stable, non-baryonic, what is called cold dark matter, and some other, let's say, more minor things. But if you look at this list of characteristics for the dark matter particle, you will see that axions and in general action-like particles have these characteristics. Plus, there is an additional bonus that some of these cases may be the most popular, and for a good reason, is the QCD axion that actually solves a problem in the standard model. So there is a connection with beyond the standard model theories with a good motivation. So axions and axion-like particles are, in principle, very good candidates for dark matter. On the other hand, you have the standard cosmological history that we understand that we cannot really directly test it. We can only put bounds for direct bounds for temperatures below 10 MeV from BBN. But other than that, we don't really know much. Now, this could change with gravitational wave cosmology and all this stuff, but it's still very early to say. And on top of that, you have theories and models beyond the standard model that can easily produce a non-standard cosmological history. And of course, you have the very optimistic view that if and when we detect dark matter, the interactions of dark matter and the way it was produced due to these interactions can kind of open a window indirectly in the early universe. So knowing the interactions of dark matter and computing its, let's say, Rayleigh density, we can find out if dark matter was influenced by some non-standard cosmological history, and so indirectly test, to some extent, the evolution of the very early universe. So this is the basic motivation that you could read in any of the papers dealing with axioms and non-standard cosmologies. Now let's talk a bit about the motivation for the code. So in the standard misalignment mechanism, you basically have to solve for this theta here, which is the some kind of rescaled axion field. And as you can see already, the equation looks kind of horrible. You have the Hubble parameter that in general is not analytically known. You have a non-standard cosmological history, and you have the mass of the axion that in principle depends on the temperature or time in general. So in order to solve this, the usual approach is to make some assumptions to simplify these equations and basically use what is called the WKB approximation, where you linearize the equation by assuming that the axion field is always small, and then you can assume that it has a sharp cutoff where sharp threshold, let's say, where before that the axion evolves like with a zero velocity, and after that it oscillates, which is generally kind of a bad approximation and not very accurate when you put everything down and you put the numbers and make all these calculations. Additionally, you have a non-standard cosmology that is described by a set of equations that look like this. You have the known stuff, that is the entropy density of the plasma, and then you have additional things that can come from an extra fluid with like a specific equation of state and a decay that characterizes how much of this fluid can decay to the plasma. And usually, what we do if we don't use a computer is an instant decay approximation, that you assume that you have a universe that is dominated by this fluid, but the fluid doesn't deposit any entropy in the plasma. And then there is a time where all the energy of the fluid is transferred to the plasma. Generally, again, this is a bad thing, and what you need to do actually is to solve these things using a computer in principle. So before showing the specifics of the codes and how to use them, there are also kind of softer reasons for having like a standard tools to do even seemingly simple computations. So the first is reproducibility. If you have a standard tool that everyone uses, or if you have a couple of them, even better, then someone can take your paper, take the code, reproduce the result, and maybe play with the parameters to get something similar. And the important thing here is that you basically reproduce the result of the paper without reproducing the effort that the original authors put into writing the paper and making all these computations. It increases confidence to your output and in science in general, because if everyone can agree on the result, and if everyone can agree with the method used, then you are confident that the results are at least correct to some extent. It also increases transparency, so what you say is, to your best of your knowledge, correct, and you can explain how you did your computation, and others can take the code, deconstruct it, see what the assumptions go into the code, and generally make the process more transparent and more accessible in general, because there are people out there that are not researchers but have interest in physics, but the threshold of entry to understand the papers is high. But if you have a paper that comes with a standard code, people in general can see how you got the results and get their own play with the physics and learn this way, because at the end of the day, we do science for everyone, not only for us. Okay, that's it. How, in general, these things are made? I try to make them as minimally as possible. Basically, both MIMES and NSC++ are based on two other libraries I have developed. The first one solves systems of differential equations, both stiff and non-stiff. And particularly this one, you can, if you have, for example, a Rangi-Kuta method, but you don't want to write an entire library, you can just input the parameters that characterize your method, and you have your method already implemented. So it's very flexible, like framework for solving differential equations. And then the other libraries for making different interpolations, nothing fancy, just a standard interpolation library that can give you interpolation of a function and its first two derivatives. And this is helpful when you want, for example, to interpolate the relativistic degrees of freedom of the plasma, which comes in every type of equation that you have that describes something in the real universe. So the other reason for doing this is to guarantee that there will always be compatible versions of these libraries with MIMES and NSC++. Basically, you will never end up in a situation where you will either have an outdated code or a broken one. These things make also the MIMES and C++ to some degree modular, because they are built simply. You can extend them and make them fit your needs in principle, if you know a bit of C++, that is. And they are independent. So I don't rely on Mathematica or any external package that could break the code with a new update or something like that. And another reason is that you basically only need a C++ compiler. So if you have a smart toaster that runs Android or something like that, you can actually simulate things in that. I don't know why you would do it, but no one will stop you to do it. So how you get the codes? You just open a terminal, you run this, and you get a copy of the code, both for MIMES and C++. Then you go into its directory, you run configure, and basically that's it. You can import both of these libraries to a C++ file. These are header-only libraries, so you don't need to install anything. Then you just compile your code and it should run. But if you don't like C++ and you just want to use Python, you just run makelib, and you can now import both of these libraries in your Python scripts and run it like that. Both of the libraries come with a lot of examples. both in C++ and Python. If you want to compile the C++ examples, you can just run make examples and you have access to the examples. And the good thing here is that you can modify the examples to do whatever you want to do, and then you can just run make, and it will just compile your modified examples. And basically, that's it. But now, from the physics point of view, what's the thing here? How do they work? So first, we have to take a closer look at the axioms. I would argue that this is more important because the non-standard cosmological evolution is kind of easy, just a simple system of kind of linear differential equations, nothing very difficult there. But the axioms are actually very difficult because they can oscillate, they can have a very non-linear behavior, and this needs kind of special attention. So if you look at this problem, you will realize that in general it's very hard. And you can see that it's hard because it's basically the classical analog of this would be a time-dependent pendulum, where both the frequency and the friction depend on time. So in general, there is no closed form solution. There are no constant of motions, but this is not exactly true. And maybe worst of all, before MIMES, there was no way to automate this process. Every time you had a new problem, you had to write new code. So what MIMES does is simulates the evolution of the axion or axion-like particle in the early universe for any kind of mass that you have. So basically any type of axion-like particle, and for basically any cosmology, with some assumptions, but this is mostly true. So what we expect from this equation? First of all, we expect to have some kind of initial condition that we can compute. It's a differential equation, so somehow we need to have initial conditions. After the initial condition, there should be some type of nonlinear evolution, again, of course, because it's a nonlinear differential equation. But what we actually know from dealing with cosmology and with similar things, evolution of scalar fields in the early universe, is that at some point they oscillate harmonically. So basically, they behave like collections of non-relativistic particles. So the last thing is actually very important, and we will see how we can quantify it better. But first, we have to assume something for the initial condition, and this is what basically defines the standard misalignment mechanism. The basic assumption is that there is one point in the very early universe where the velocity of this field, its first derivative, goes to zero. And you can either see it from the equation directly, or if you write down the Lagrangian of the action field, you will see that there is a shift symmetry that basically says that the derivative should go to zero relatively fast. So the initial condition that you can use is that the derivative of the action field is zero at some initial time at some high temperature. Basically, when the Hubble parameter is much bigger than the mass of the axion, and that's it. Then you only have to specify the initial condition for the field itself. And this is in principle a random number. Because if you think about in the early universe, the action field kind of rides on top of the inflaton or something like that, behaves like a spectator or something very similar. So in principle, it's a stochastic field and it has a random emission condition. So this is just a detail in the code. You don't specify the temperature at which you start integration. You specify a value for this ratio, basically the Hubble parameter of the mass. You choose some large number, typically around 1,000, seems to work very well. And then automatically the code finds a suitable initial temperature, and it runs like that. And this seems to be a bit faster than choosing an initial temperature. This is the only reason that I have used it. But as I said, you can change it kind of easily because the code in principle is very simple inside. Okay, now the actual reason I published this library is the stopping condition for integration. When I had a similar project where I had to solve this equation, my main problem was where do I stop integrating? Because I know that at some point the oscillation will become harmonic, but the problem is there are two problems. Do I stop at some random point that is very late so that I can kind of guarantee that the evolution is harmonic? And if I do this, then how can I make sure that the code actually works? Because what happens is that the oscillation frequency increases as the universe evolves, as the Hubble parameter falls. And with very rapid oscillations and very small values for the axion field, you can end up in a situation where the differential equation becomes very oscillatory and your code basically cannot handle it. Any Runge-Kutta method has a breaking point. And so you need to find a condition that minimizes the chance of this happening. And this came from the adiabatic invariant. So the adiabatic invariant is something that usually is defined in, I don't know, second year physics course where you study Hamiltonians. So if you have a system that exhibits closed orbits, if the Hamiltonian varies slowly compared to the period of this motion, then there is a quantity that is almost constant. And this quantity takes this form, is basically the integral over a closed orbit of the momentum integrated over the conjugate position anyway. So, and you can see that it's actually, its derivative, it's suppressed if the Hamiltonian, if the derivative of the Hamiltonian is much smaller than the period. So basically, that's it. And how do you exploit this fact? How do you write down this, and how do you exploit it for the axion? Is basically straightforward. You just have to find a Hamiltonian for the evolution of the axion. This doesn't have to be the actual Hamiltonian. This just has to be a Hamiltonian that gives you the same equation of motion. The maths are the same. It doesn't matter where they come from. So if you have a Hamiltonian, you get for free under certain conditions an adiabatic invariant. And the adiabatic invariant for the axion can be written like this. And now you take this integral that is in a closed orbit and you go from the minimum to the maximum and you double it because the period, the adiabatic invariant will be constant within a period, so it doesn't matter where is the minimum and the maximum. Basically, you solve for the momentum, you write it like this, and the crucial point is to remember that the Hamiltonian is constant within this closed orbit. So because the Hamiltonian is constant, instead of theta here, you can have the maximum value of theta within one oscillation. The maximum value of theta is defined where the momentum is zero, and you get this simple formula, relatively simple formula for the adiabatic invariant. And the good thing is that this holds for any type of axion field. So you compute it once and you are done. Now, how does this help with defining a good stopping condition for integration? You just check that the adiabatic invariant is invariant from one peak to the next. And if this happens enough times, then you stop integration. And how much is close enough and for how many peaks this has to be constant, it's up to the user to decide. You have two numbers that you put in the code, and this define your stopping conditions for integration. Then from the physics point of view, what you can do is you can say, okay, sorry, I know that this is constant, so I can write down also the energy density of the action today at some peak of the oscillation, and then I rescale the theta peak that would appear in the energy density of the action. I rescale it so that the adiabatic invariant is constant. And what this gives me is a relation between the peak of the axion field today with the peak of the axion field at some arbitrary point where I stopped integrating. Then I put this theta into the energy density for the axion, and I get this formula that you can probably find in a lot of different papers. Also, you can include an entropy injection factor just to make sure that you can actually use this formula in any type of, not any type, but a lot of different types of alternative cosmologies. So that's it, basically. We can sum up the assumptions that MIMES makes. So to choose a good initial condition, you have to make sure that in your scenario, the Hubble parameter over the mass increases monotonically with the temperature. This is typically true. I haven't seen a case where this is not. But again, if you have a scenario that doesn't follow that, it's relatively easy to change the code itself. Then you assume some initial velocity to be zero. You have to assume, unfortunately, at least for the moment, that the axion is always subdominant. If it dominates, then you need to solve a system of equations and things become a bit harder. But I don't see a reason that you would want to do this because at the end of the day, you want the action to be the dark matter today, or at least a component of dark matter. So it has to be kind of small in the universe. Also, you assume that the evolution of the action is described by the equation of motion that we had before. Nothing more. No extra contributions from any other type of production of the action. And because the equation is nonlinear, this cannot be, in principle, it's not straightforward to add. So that's it, basically. Now we shift back again to the coding side of things. What do you have in these two libraries? You have a Cosmo class, both in MIMES and in C++. This class is basically responsible for making different interpolations for the different quantities of the plasma, like the relativistic degrees of freedom, the energy density of radiation, the Hubble parameter, the derivatives of these things, and different constants that you have, like the Planck constant. Everything is in this Cosmo class. You have the axion mass class, where you can use it to define the mass of the axion that you have. You can either give it a list of numbers and it will interpolate it, or you can just give it a simple function. The code itself comes with values for the QCD axion, basically the mass for different temperatures, but you can either change this file or import your own file, and it should work without problem. Then you have the axion class that you use it to solve the equation of motion. And for the NSE++ library, you have the evolution class that solves the equations that describe the evolutions for the entropy of the plasma and the energy density of the fluid. Now, these are details. You need to input a lot of things in these two libraries to work. I try to make it as customizable as possible. So in both of these, you need to add to include probably around 12 different parameters, both describing the physics and how the Runge-Kutta integration actually works. So, for example, you need to specify the axion mass. You need to import a file that gives the Hubble parameter, the scale factor at different temperatures, a value that will be used to determine the starting point of integration for the evolution of the axion, and the condition for stopping integration. And you have other different things for the non-standard cosmologies, like the equation of state for the fluid, the decay rate of the fluid, initial conditions, and different kinds of temperatures, including a temperature where integration will stop no matter what. This is just a fail-safe, basically, in principle, that integration continues way beyond whatever is natural. For example, if you have a fluid that dominates the energy density of the universe below 10 MeV, this is already excluded and you don't really need to continue integrating. So we can just put a hard cutoff and stop integration there and just ignore the result. You have different template arguments. These are now, we go into details that are not extremely important. What is important is that you already have a good selection of different Rangi-Puta methods that you can use, and you can choose any of them, or you can just give it some parameters to define your own, and in principle it should work. And in the paper, I describe how to do this. So I hope it's clear, and you can use it if you need it like that. And you don't even need basically to go into C++. You can just modify these definitions file that I have, both in Minds and C++, that can do these things for you automatically. So you just have a configuration file that defines all these, and then you just modify the examples I give, and basically the code is ready. You don't need to actually write hardcore C++ code, or you can just use it using Python, and it's fine. So I think we are kind of running out of time soon, so we can go to examples. Don't worry about this, but instead of giving you the examples, maybe it's a good idea to actually run it in real time. Hopefully it will work, otherwise it will be very embarrassing. So you can see that you have a code in Python. This basically is the one case for the axiom. You can you define everything in just 42 lines of code. The important things here is that you can like define your mass, and in this case, I import the data from Lattice for the QCD axiom mass, like this, like you just import a simple file from Python, and it works. Then you can define, because your file will have a minimum and maximum temperature, you can define what happens beyond this. Usually you can put like the mass to be constant outside of the limits of the file that you give, or you have some analytical approximation that you can use. For the QCD axiom, for extreme cases, we have some analytical formulas for the mass, so you can just write simple functions that describe what happens when you try to interpolate beyond the limits of this file. Then you specify the file where you have the data for the cosmology. In this case, I have like a matter-dominated universe already created. After that, you just define your axion instance with this a lot of parameters, and you just solve it. And once you solve it, you have access to everything. So we can basically we can go to this part and copy this line. Basically, I already have done this, so we can get mines. Should be fast. Can you see my screen or no?
I can see your screen.
Okay. Can you see the terminal or the?
No, I can see.
Okay. Yeah, that's the Zoom thing. So let me change. Okay. So hopefully now you can see the terminal. I already
Yes.
I already run this command, and mine seems to be here. Then I can do the same thing for the non-cosmological thing, and it's here. And okay, so I just realized that when I talked about the code, you couldn't see the code, right? So
No.
yeah, okay. Since it's Friday afternoon, I can spend a minute again here. Now you can see the code,
Yes, indeed.
hopefully. All right. So we define the mass in one line of code, like importing a simplify. You can do the same thing by writing a function if you have an analytical form for the action. And then we can define the behavior of the interpolation beyond the limits, the temperature limits that you have in the file that you just imported. And in this case, for the QCD action, we have some analytical approximations for some extreme temperatures, so you can use these as simple functions. And after that, you can specify the file where you define the cosmology, in this case, a matter-dominated case. Then you define the action, you solve the equation of motion, and then you have access to everything you might need. And since we are here in the code, we can do exactly the same thing in C++. Hopefully, the code is not very different than in Python. I spend a lot of time trying to make the two codes, let's say, look similar. So the action mass is defined again in one line. You don't need to do anything. You have these ugly namespaces in C++. You can get rid of them, but I like to keep them here for clarity. But other than that, I think they look very similar, the C++ and Python code. The difference is that you need to compile the C++ file every time you change it, but with Python, you just modify it and run it. Similarly, for the non-standard cosmology, you can write the code in Python or in C++. Again, the two seem almost identical. C++ again has a bit of more it looks a bit more busy due to different things that you need to write, but other than that, the way you use it is exactly the same. Okay, so since we have hopefully seen the code, I can return to the terminal and you just run these two commands and you have the two libraries. Then you can go to each directory, just run configured. Now MIMES is configured. You can go to the other one, run configure, and then a C++ now is configured. And the only thing now that you need to do, let's say if you have a C++ code, you can open a terminal, compile it. Compilation, it's not very difficult here because this is just a new header that you put. There is nothing else that you need to do. So the directory that I have these codes is code. And then if you run G++, you can run Clang or any other compiler.
Sorry, I think you are still in the old, the screen share is in the old screen share.
Okay, yeah.
That it is showing ends.
Yeah.
Like, okay.
I think there is a way. If it worked, it would. No, anyway. So you go to the directory where you have your code. You can open the examples that come with the libraries. But since I have this simple thing here, I can show you how to compile it without running make or anything like this. So you just run G++ as a simple, as you would in a simple case. The only thing that you need to specify is where the root directory of mines is. In this case, is one directory up and then mines. Now, it's good usually to do this all three. This makes the code kind of faster. This is the optimization level of the compiler. It doesn't really matter what it does. It matters that it makes the code kind of faster. And it should compile. Yeah. Now it compiled, you run it, and you can see that the code took like less than 0.1 seconds. This is the time that it took to run. And this particular point I chose gives you a relic abundance close to the observed one. And you can then extract information related to the evolution of the action. Usually we are also interested in the temperature where the oscillation started and the value of the action when the oscillation started. And you can extract different kinds of things. You can extract the error of integration. You can extract the error of integration for every temperature, but this is kind of you get it when you start to explore it, just to make sure that the code works and the results that you get are correct. Anyway, you can do the same thing for if you want to run the non-standard cosmology thing. Exactly the same command, basically. The only thing that changes is the name file and the root directory of NSC++. And of course, it didn't compile. And that's embarrassing, and that shouldn't happen. Anyway, we should continue. Although it's very strange. Anyway, it doesn't matter. Let's say that it worked. And the alternative to this, if it doesn't work in your case, which if it doesn't work for me, it's very probably. You can go, let's say, to NSC++. Now we are in this directory. And you can run make. Takes a minute. It gives some warnings. The warnings don't really matter. And make now compiles everything. It compiles the examples. It compiles the libraries, the shared libraries that Python uses. And basically, you can now use NSC++ in Python, or you can run the examples. You can do exactly the same thing with mines. You can always parallelize make to make it a bit faster. And again, it compiled fine, and hopefully you can now go here, use Python. And now what this did is it basically solved the coupled equations for the entropy density of radiation with the energy density of the fluid for some parameters. And this is basically the evolution of these two quantities for, I think, for different scale factors. Now, from the scale factor and the entropy density, you can extract the temperature, and then you can extract whatever you need from the cosmology. You can extract the Hubble parameter and any other thing that you need. Then you can interpolate this. You can take the derivatives. You can do whatever you want with the results that you got. And you can do exactly the same with the axiom. And if you see now this yeah, again, I'm really sorry. That's why I don't like Zoom. You missed again the examples, right? Okay. So, as I said, you can just use Python to run the non-standard cosmology, and you get a bunch of numbers. Now, this is the actual evolution of the system of radiation, the plasma, and the fluid that you have inputted for different scale factors. And you can do the same for the axiom. And if you compare the output of the axiom that you got from Python and the output that you got from C++, they are basically identical. And why I'm showing you this is because this is the time it took for the Python script to run, which is 0.09 seconds, and it took 0.06 seconds for C++. So there is a kind of trade-off. If you use Python, your code will be a bit slower than C++, but at the end of the day, it's up to you. It's easier to use Python for a few things, for example, but if you want to scan an entire parameter space, maybe you just want to run the code using C++. So these were the examples. It didn't go as smoothly as I would hope, but again, Friday afternoon, I'm sorry. So let's return to finish this. So we saw the examples of the code, and then we can see some general results that you can get. So you can simulate different types of cosmologies. For example, you can see here, this is the entropy density of the entropy over the entropy assuming a radiation dominated case. And for different temperatures, for high temperatures to small temperatures, you can see how entropy injection happens in different cases. So you can have an early entropy injection, a late entropy injection. You can have different kinds of things. The size of this, you can define it. It doesn't really matter. The code works for everything. And you can also simulate different kinds of silly cosmologies. This is some type of kination, for example, where the Hubble parameter is always much larger than the radiation-dominated case. Or you can have other things where you start at radiation domination, then the fluid dominates, then it decays, and you have radiation domination at the end. And keep in mind that at the end, you should end up with a radiation-dominated universe because you have strict constraints from BBM. So this is the common factor that all these cosmologies have. From the action side of things, again, you can do different kinds of computations. You can simulate the QCD action. I think this is the QCD action in the radiation-dominated universe. And the red line is some random kind of action with, I believe, with a constant mass. And you can see again that you can get different kinds of behaviors with different end results. And beyond this, you can also see how the evolution, how the derivative of the action field evolved. So again, you start at relatively very high temperatures where this goes to zero. And at some point, it starts to move away from zero, and then it starts to oscillate like a typical oscillator with these types of characteristics, basically a time-dependent friction and a time-dependent frequency. You can have combinations of both. So this is the evolution of the QCD axion for radiation-dominated universe, early kination domination, and early matter domination. You can see three kind of distinct types of behavior. You have matter domination that gives the smallest result because there is a period of entropy injection, and this affects the redshift of the axion. Then you have early kination domination that gives the larger result because the oscillation basically starts earlier compared to radiation-dominated case. And for the radiation-dominated case, you have something in the middle. Now you can take this and you can scan all these parameters at different initial conditions, different types of cosmologies, and get a plot like this. This is the initial value of the axion field, and this is the mass of the axion today. Again, this is for the QCD axion. In the middle, you have the radiation-dominated case. I think this is the usual curve that you can find in different kinds of papers, but you can extend this and see that the upper half likes cosmologies that are close to matter-dominated universe, and below this curve, you have the preferred cosmologies basically look like kination. Okay, so we are almost done. We have seen MIMES and NSC++. They can do different kinds of things. I have argued that they are flexible, but it's up to you to decide. It should be relatively easy to use. They should give you good results. I have tested them extensively against different results from different papers and some analytical computations. Everything seems to be fine. Of course, if you have an issue with the codes, with the results, you can always contact me. I'm happy to talk about this for days if you have the time. And in my opinion, because it's easy to use, there is no reason that you need to do approximations for these things. You just download the codes, run them. The codes are transparent, the papers are also transparent. So they also give you a good idea of exactly how the code works under the hood. So you shouldn't have a lot of questions on how did you get this result and how did you get that result. Everything should be clear. And again, if something is not clear, you can contact me. I can probably have a discussion with you about this. And for the future, and this is actually something I'm trying to work on, is to make fewer assumptions in general for both cases. This means different types of initial conditions. For example, there are other types of misalignment uh, for the QCD, like the kinetic misalignment, where the initial condition is different. There are other types uh, of evolution where you have an extra friction. So this also would be a good addition. And there are other things that you can do, like an extra decay of an extra source of action, so something like that. And similar for the non-standard cosmologies, you can have different types of fluids. Maybe the easiest to implement is time-dependent decay width and time-dependent parameter for the equation of state, but you can make it as complicated as you like. And in principle, it would be good to have a combination of both of these, like solving for the non-standard cosmology in real time when you try to solve for the action. This will give you, if you want to have the option of having an action that dominates in the early universe, for example, if you have something similar. Something else that could be useful is like on-the-fly constraints. There are packages out there where you can put results from your action model and it automatically compares with experiments and also makes automatically some plots. So it would be good to have some connection between these two. And then for the long term, MIMES can become like a general scalar equation of motion solver that can deal with different types of situations, including particle production, including actually simulating the field. Instead of simulating the field in terms of its energy density, you can simulate a field if it is described by a scalar field. You can simulate it using the future version of MIMES. You can add particle production like parametric resonance and stuff like that. And then you can keep adding things on top of that, but this is well in the future. So this is it. Thank you for your attention. And you can scan the QR codes and get the two libraries, and hopefully we have fun and be productive with them. That's it.